Yeah, let's start from this formula. Yeah. This formula comes from our textbook. Yeah. And it's a very interesting formula. Here you can see, what do you see? The matrix multiplication. It's a matrix property. Yeah. And this is the key property for this new algorithm. Yeah. And this property, we know matrix multiplication is more complicated than the regular multiplication, right? It's quite different from the regular multiplication, more complicated. So it looks like because for the calculate Fibonacci numbers directly, we do regular additions, right? We do not do multiplications. We just do additions, right? Okay, yeah. Here it looks like with this new property, we convert to regular additions to matrix multiplication. Operations. More complicated, right? Yeah. But the good thing is, yeah, look at the right-hand side. And it's a matrix power form. The matrix is a simple one, 0, 1, 1, 1, 2 by 2 matrix raised to nth power. Yeah. So here you can see we have a new representation of Fibonacci numbers. Yeah. Left-hand side, the 4 entries, we can use appropriate Fibonacci numbers. The right-hand side, it is a exponential function of 2 by 2 matrix. The base is a matrix. Exponential function. Yeah. The good thing of this property is after this conversion, a big O algorithm can be converted to big O of log of n. Because when we calculate matrix exponentiation, we can use repeated squaring, right? Remember, repeated squaring. So by the repeated squaring technique, we can get big O of log n efficiency. That's a big improvement. From big O of n to big O of log n, that's big improvement. Remember, big O of n, if we do the search, it's linear search. Big O of log n, that corresponds to the binary search. So here, how big is the improvement? That's just like from the linear search to binary search, that kind of improvement, how big it is. Okay, so that's why this algorithm is very valuable. Okay, yeah. All right. To understand this algorithm better, so let me review the matrix multiplication a little bit. Yeah. So I hope most of you know about matrix multiplications. Yeah, but here I just review a little bit. So we do 2 by 2 matrix multiplication. Yeah. Now let me use the first matrix A1, B1, C1, D1 for 4 entries. Okay. The second matrix, we use A2, B2, C2, D2 for 4 entries. Okay. All right. Then the result matrix, the product. Yeah. There is a formula so we can use. Here, let me just review. Yeah. Suppose A, B, C, D. Yeah. Suppose the result, let me use X, Y, Z, W. Okay. Yeah. Then X, this entry equals row multiply column. Yeah. So A1, A2 plus B1, C2. Y, this entry, the first row of the first matrix multiply second column of the second matrix. So A1, B2 plus B1, D2. Y. Z, this time, the second row of the first matrix multiply the first column of the second matrix. So C1, A2 plus D1, C2. Okay. Yeah, the last one, W entry, second row of the first matrix multiply the second column of the second matrix. C1, B2 plus D1, D2. Yeah. So if you know these formulas, how to calculate the 4 entries of the product 2 by 2 matrix, then you can do the calculation. All right. Yeah. Although a little more complicated, but if you just write the formula, run your program, so it is not too hard. Yeah, it is not too hard. Yeah. All right. So this gives you the way to calculate 2 by 2 matrix product. Yeah. The next question is our goal, we want to calculate this matrix exponential function efficiently. The next question. The good thing is we have the lot of repeated squaring experience. So remember, in module 1, we spent a lot of time, Horner's rule, repeated squaring, repeated cubing. So we have a lot of experience. So here we can borrow that experience. But when we borrow, it's not a repeated squaring on regular multiplications. This time we extend this technique to matrix multiplications. And that's okay. The same idea, so we can easily extend it to matrix multiplications. Yeah. Here, let me use the next slide to explain how to extend it to matrix multiplications. Yeah. Here in our textbook, there is topic very close to this one. It's called a binary exponentiation. On page 236, there is a topic called binary exponentiation. Exponentiation, yeah. A person. All right. Yeah. But that one still on regular multiplication. It's not a matrix multiplications. Yeah. But we can borrow that algorithm. Yeah. Here, let me explain. But actually, I do, the algorithm on that page, actually, I do not recommend that one directly to you. Yeah. Because we can do easier than that. Yeah. So the binary exponentiations, that implementation not as easy as the recursion approach. Yeah. We can do the recursion approach. That will be much easier than the algorithm on our textbook. Yeah. So let me talk about the easier way, recursion way. Yeah. All right, so let me use this slide to explain the recursion way. So this way, more straightforward, easier to understand. So when you write implementation, much easier. Yeah. So recursion implementation. For binary exponentiation. Yep. Yeah. So here, when we do binary exponentiation, our version here different. We do matrix version. Matrix version. Binary exponentiation. So here you can see with some related knowledge pieces, we put things together so we can find a very good solution. Yeah. All right. Here in the textbook, it used the binary exponentiation to calculate a to the nth power. That little a, arbitrary real number. Okay, arbitrary real number. Yeah. Here, so let me describe it as, because we need to extend it to matrix version. Yeah. Let me call it capital M to the nth power. Our M here, so it is a 2x2 matrix. Okay, yeah, yeah. But idea the same. Okay, idea the same. All right. So we can define a function in the recursion way. Okay, yeah. So let's call the function, yeah. So this function will return another 2x2 matrix. Okay, yeah. So let's call it this function. Let's call it expo of m and n. How about that? Yeah. Two parameters, base matrix M and the exponent number n. Yeah. Then when we do recursion, first we look at the base case. If n equals 0, yeah, base case, n equals 0, return so what is n to the 0th power? It's identity matrix. In matrix, yeah, because we not use 1, right? Yeah, little a to the 0, that is 1, right? Yeah. But for matrix, it's an identity matrix. So what's the identity matrix? 1, 0, 0, 1. Yeah, that's the identity matrix. So return the identity matrix. Then identity, yeah, 2 by 2 identity matrix. Okay, yeah. If n equals 1, another base case, return n, right? Yeah, because itself, n to the first power equals itself. Okay, yeah. All right, so then after that, yeah, after that non-base case, yeah, so let's consider else, okay. Else, we can do recursion, yeah, but when we do recursion, let us use a variable product equals, we call this function m. How about that? Yeah. N over 2 floor function. Yeah. Recursive call product. Okay. Yeah. So this is the recursive call here. Then we check if n mod 2 equals 0, that means it's an even number. Return product times product. Matrix multiplication. Yeah. So this is another matrix multiplication. Matrix. Okay, yeah, another. Then the remaining case, odd case, right? Or you just use else, okay? Odd case, return product, multiply product, then multiply another extra m. How about that? Because odd case, you need to do one more matrix multiplication. Yeah. Yeah, actually you can calculate. Yeah, so you can calculate product by product. All right. Yeah, but even case, you just return that product. For the odd case, you need to multiply an extra m on top of it. Yeah. In this way, you can implement matrix binary exponentiation. Okay. after you get, because after you get the result matrix, so that is f of n minus 1, f of n, f of n, f of n plus 1, you can extract, f of n from this position or this position. Yeah. Same value. That's your Fibonacci number, the final answer. Yeah. So this way, you can get bigger of log n solution. Yeah. It should be faster than the, the previous solution, bigger of n. Yeah. But when you do comparison, so in your program, when you do comparison, only when n is a very big number, then you can see this log algorithms performs better. Yeah, because if n is not very big, then probably the linear one is faster. Because when we do matrix multiplication, we spend more time, right? More complicated. Our matrix multiplication will usually much slower than regular addition operations. Yeah. But when n is really big, yeah, here I do not know how big, you can see the big difference. Yeah. You can do experiments, but eventually the log algorithm will be much faster than that linear algorithm. Okay, all right. So that's the option, that part. So this one, if you can understand, first you need to understand the whole description I gave you here. Yeah. Then you can write a code to implement. Yeah. And we know here, when we do implementation, all this exponentiation, we need to use Java big integer to do it. Java big integer version. Yeah. Each matrix entry, you use Java big integer. Okay. Yeah. You may need to define a special Java class to represent a matrix. How do you represent a matrix, right? Yeah, so you need to consider, define a new Java class. That Java class, you use it as a data structure to store 2x2 matrix. 2x2 matrix. 4 entries. You need to represent 4 entries. Each entry is a Java big integer object. Okay. And then you can define matrix multiplication method in that class. Matrix multiplication. Okay. Yeah. Yeah. So then later, when you need to do recursion, binary exponentiation of matrices, you just call that matrix 2x2. 2x2 matrix multiplication method in your matrix class. Okay, yeah. So you need to do some work. Okay, yeah, based on this idea. After you understand it, you need to do some work. Yeah. Then, the reward is also pretty good. The reward is you can get 3% extra credit. Very significant. Yeah. All right. So worth a try. Yeah. If you need my help, I can give you more details. Yeah. Here, I give you the general detailed description, general idea description. So when you implement it, so you feel, in some steps, you need me to clarify it. Yeah. So then I can explain a little more. Yeah. All right. Yeah. But only when you cannot find enough time. Yeah, that's possible. In the final, you have many courses you need to worry about. Yeah. So then, because this is an option. Okay. Yeah. Yeah. All right. So I like to stop at this point. If you have any question, you can ask me. If not, I like to move to the next topic. Yeah. Our hash function, our hashing technique. Yeah. All right. So here, let me continue from what we left last time. Probably many of you, I need to refresh your memory a little bit. Yeah. So last time I gave you short introduction. Yeah. I use the existing search algorithms to do comparison. Linear search, binary search, and another one, less popular, most people do not call it. It's called index search. Because most people, they do not treat it as a, legitimate search algorithm. Why? Because too restrictive. The reason this is not a good search algorithm, too restrictive. Yeah, I will explain why it's so restrictive. Yeah. Nobody really uses it in the real world. But the reason we put it here because it gives us a starting point for the hashing technique. It's a nice starting point. Okay, yeah. So it has some very interesting idea to help us get started for this hashing search technique. Yeah. So let's see. First, we like to see the limitation of this search algorithm, index search limitation, huge limitation. Yeah. All right. Oh, yeah. In our textbook, or in some of the algorithm textbook, another name for it called direct addressing. Yeah. So this name, its formal name called direct addressing. Yeah. Why direct addressing? Give an index of an array element. That's the direct address, right? Yeah, that's the address. That's the location of that element. So you can go there, find the element immediately. So another name, official name for it, direct addressing. Yeah. All right. Yeah. So whatever name it is, yeah, the same idea. So that's our starting point here. Okay. Yeah. So let's look at this key property. Yeah. The key property here is given a key, a search key. Yeah. For any search algorithm, we need to have the search key first. What is the search key for this special situation? Index of an array element. That's the key. Yeah. So here you can see one-to-one correspondence. For each key, there is one position in the array that corresponds to the given key. Okay, yeah. Now, the main problem. limitation. Yeah. When the keys are long, yeah, think about the keys are long. Yeah. So later we will see why we may have many real-world situations. Our search keys could be long. Yeah. So we need to consider real-world situations. Yeah. When the keys are long, but you only have a small number of elements in the array. Yeah. So this situation is very common. Yeah. In the real-world applications, this situation is very common. Yeah. I will give you a simple story in the next slide. Yeah. Then you have trouble here. Yeah. You have the trouble is this method would waste a lot of space in main memory. Yeah. So that's not efficient. That's the biggest limitation of this algorithm. Yeah. All right. So let me use another simple example to explain this limitation problem. Yeah. How to use space efficiently. Yeah. When we look at this special example, we need to think about how to fix it. Yeah. We don't want to throw it away. Yeah. There is some good property for it. So we still want to use this idea, but we need to improve it. Yeah. All right. So the long keys. Think about when we want to store the information of students. Yeah. Usually we use SSN or student numbers, right? How to identify a student. So you can imagine a better way. Yeah. Currently, yeah, because we don't want to use social security numbers directly, right? Yeah. So we like to use the student numbers. And you can see how many digits do you have in a student number, right? So it's a long keys, right? We can treat it as long keys. Yeah. Then suppose we need this many digits in a typical student number. Yeah. Then suppose in a class here, let's consider a class with 40 students. Okay, yeah. That's not a big number, but quite reasonable, right? Yeah. So yeah, 40 students. So when you store the information of these 40 students, you need 40 slots, right? Yeah. This array, you only need to create 40 positions. Yeah. But here, you need to use student numbers. Can you use student numbers as the indices of an array, right? If you create an array of objects, think about this, array of objects. And if you use the direct addressing or index search, because you want to search student information very fast, then the long keys would cause problem. Long keys, if you just make your long keys correspond to the array indices, then you would waste a lot of memory spaces. Huge amount of memory space will be wasted because you only need 40 slots. But the long keys, you need to use large number of array positions in the main memory. So that's the reason this method is not used in the real world applications. Too bad. Yeah. All right. Now, our next question, how to use space efficiently. Yeah, if we can fix it, then we can modify this approach, this method, modify to make it useful. Yeah. So you can think about, is it possible we can so here, in this example, we only need to declare 40 positions in main memory, 40 positions. We do not want to use more than 40 positions. Okay, yeah, 40 positions, but we use the long keys. We use the student numbers, long keys, as the search keys. Okay, yeah. They are not array indexes. Yeah, we change that. Array index, that meaning we will change, but we keep those long keys as the search keys. Yeah, because the student numbers, they are very natural search keys, right? So we don't want to change that part, student numbers. Yeah. But we want to map those student numbers to 40 slots. Think about that. Yeah. We only have 40 slots in main memory. So we need to do some mapping. Map student numbers to 40 slots. How about that? How about that idea? How about that modification? Yeah. Here you can see this improvement idea. You see some special mapping, right? Some special mapping between student numbers and the number of slots you need to use to store your data. So this mapping idea is critical here. Is the main point of this new search algorithm. Mapping, how do you do the mapping? That's the key. Yeah. So we will study the mapping details. Then a new search algorithm can be developed. That's the hashing. So the mapping, that's the essence of this hashing technique. Okay, all right. Next, we will study what is a good mapping. Because there are so many different ways to do the mapping. Yeah. So we need to choose better way, better mapping ways. Yeah. All right. All right. So as a conclusion, so we summarize our analysis points. So we cannot use long keys as the indices directly, but we can change that. Right? Yeah. So the solution is how to make keys shorter. Okay. So how to design your mapping functions to make the keys shorter. Yeah. So now our implementation idea becomes how to design mapping functions. Yeah. Mapping, we know we use functions to do mapping, right? Mapping functions. How to design mapping functions to make those long keys shorter. There are so many different ways. Some of the ways are good, some of the ways are not good. So we need to study that. We want to avoid bad mapping functions. And we want to choose good mapping functions. Yeah, so we will study that kind of details. All right, yeah. So mapping strategy. Yeah. There are several, there are many different strategies. Yeah. So let's study one by one. Yeah. What is a good mapping? Yeah. All right. One property fast calculation. Yeah. Because when you do mapping, it takes time, right? Yeah. So you have a function, you plug in the long key into this function, and then you do calculation. And we want a fast calculation. We don't want, do some very slow calculation. It takes a lot of time to find a mapping result. Then it won't be good. Yeah, too expensive. Yeah. So the first property we like to have, fast calculation. The mapping function should not be very slow. Okay, yeah. Second property, evenly distributed among all the slots. Yeah, because the number of slots, here, let's consider, certain number of slots. Yeah. And when we do mapping, the keys, think about large number of keys when we map to the slots in this range. Is it a good way? So if we map, all the keys in a small region, that's not good, right? Yeah, map to small region. That's a bad mapping way. Yeah. So we like to, make the mapping spread evenly in this whole range. That would be the best. Okay, yeah. So that's the second property. Yeah, evenly distributed among all the slots. But to get this property, it's hard. It's hard. Okay, yeah. Then another property we like to have, not sensitive to any pattern. So what's that? Not sensitive to any pattern. The data could have some pattern, right? Yeah. The data, so that means the search keys. The search keys may have some special pattern. So we don't know. Yeah. But it's possible there is some, special pattern, unknown pattern even. Yeah. And a good mapping method, it should break any pattern, not sensitive to any pattern. Yeah. Because usually, if your algorithm cannot break certain, given pattern, then you have the situation many keys are mapped to a small portion of the range. Yeah, because the pattern will cause that. The special pattern would cause that. Okay, yeah. Later I will talk about some special patterns. So you can see if your algorithm cannot break that pattern, then many keys will be mapped to small portion of the slots, not evenly distributed on all the slots. Yeah. All right, so these properties, before we design these mapping functions, yeah, so we need to consider these important factors. Yeah. Next, implementation. Now let us try several functions. Yeah. and we want to see how good they are, yeah, as mapping functions. Choose appropriate math functions. Here we need to use math functions because we have a lot of flexibility to design different math functions. There are so many different ways we can apply special math formulas. Yeah. All right, so let us consider some relatively simple math functions. Not very complicated. If your math function too complicated, very hard to calculate the values, then it's a not good selection. Yeah. All right. So we call it this type of special math functions hash functions. Hash functions. We will do hashing. Yeah. So hash functions. We need to design hash functions. Yeah. All right. C.2, hash functions division method. Yeah. So actually, multiplication division method. So we will, compare. So let's look at a division method first. Yeah. Actually, multiplication method will be harder than division method. So when we start, let us start with relatively easy method, division method. Probably the easiest mapping function we can start with. Yeah. All right. Hash function design, division method. Why division method is easiest? Yeah, you will see very natural, the most straightforward way to map long keys to relatively small number of slots. The fastest way, division method. Yeah. All right. Assume that all keys are natural numbers. For simplicity, when we start, we make this assumption. But later we will remove this assumption. Because sometimes we can use keys, the keys could be a string, right? Yeah. Because in real world applications, many times the search keys could be strings, yeah, long strings. Yeah, we allow that. Yeah. But here at this point, so we can make numbers first, because number we can do division, right? Yeah. For strings, when you do division, you need to define what's the division meaning regarding strings, right? Yeah. Later, we can easily extend it to the string case. Yeah. So we don't worry. So for strings, we can still apply hash functions. Okay. Yeah. All right. So here, assume all keys are natural numbers. So we can do integer division easily, right? Integer division. Yeah. All right. So yeah, non-natural number keys can be converted to natural numbers easily, right? Yeah. Yeah. 26 characters. Can we imagine a numeral system with 26 digits, right? Yeah. So that conversion is pretty straightforward. Yeah. We have many ways we can do conversion. Yeah. All right. So here, let's consider the general case. There are n slots. Yeah. How to map a relatively large key K to one of the slots. Yeah, n slots. So each slot has a, small integer position number. Yeah. So usually from 0 through n minus 1, right? Yeah. If we count from 0, 0, 1, 2, 3, through n minus 1, these m positions. Yeah. So we need to do a mapping that allows us to map a long key, large key, natural numbers, one big natural number that can be mapped into this range. All right, yeah. So that's pretty easy, okay? The modular operation, how about that? Yeah. Here, H refers to hash function. So we define our hash function, H of K equals K mod M. How about that? K mod M. The result, we know, one of the slot number from 0 through M minus 1. The slot number, yeah. Any long key can be mapped in this way quickly. The operation is also fast, right? Simple and fast. Yeah. And the mapping result is a valid slot number, right? It falls in the range, valid range for a slot number. Okay, so all the requirements are satisfied, right? Pretty good, pretty neat, right? Yes. But it's a simple operation, right? Yeah, because the modular operation mod, okay, you take away the quotient, you only keep the remainder part. Yeah, because we only take the remainder part. But we basically do division, right? Modular operation and the division operation, you know, pretty close. Integer division, but we throw away the quotient part, and we only keep the remainder part. Yeah, so that's our first hash function. Yeah. But it may not be good, although it's simple, but you know, we can look at. So what's the problem from the simple hash function? Yeah. All right. Yeah, easy to calculate, evenly distributed, not quite sure, evenly distributed, because we cannot predict what properties the search keys may have, right? Nobody knows that. What kind of properties the search keys could have, nobody knows that. So you cannot answer this question, evenly distributed or not. Probably not. Yeah, probably not. Okay, yeah. It depends on the keys. If your keys have some special patterns, yeah, here we need to look at the pattern issue. Special patterns, then you may have some trouble. The simple mapping like this would cause some, you know, unpleasant property. Yeah. All right. Called by any pattern. Yeah. So we can try to look at some special pattern, simple pattern here. Yeah. All right. So let's consider some special pattern. Yeah, because our goal, we want to make hash function robust. Robust means it can break most of the pattern. You know, we cannot say break all the patterns. That's impossible. No hash function can break all patterns. All right, yeah. So the division method with M slots. Yeah. Let's imagine some special pattern. Yeah. Example 1, when M equals 15, yeah, here. This 15, this number, yeah, is a special number. Yeah. Why? Because it's a product of 3 and 5, right? Yeah. And 15 equals 3 times 5. Yeah. If we use the hash function, its definition is K mod 15, then look at the pattern. So if the pattern is K is a multiple of 3, that pattern, the given search keys are multiple of 3. Let's imagine that special pattern. Okay. Then K mod 15 is the remainder also multiple of 3, right? Because 15 is multiple of 3. So after we apply the modular operation, the hash function value h of k is another multiple of 3. All right. That means your slot number is multiple of 3. What's the consequence? Yeah, so here we know, yeah, because the hash function h of k minus k, it should be a multiple of 15. Yeah. Because we remove the 15 multiples. When we do modular operation, we can take away 15 multiples. Yeah. That's the 15 multiple, 15n, that's the 15 multiples we take away. Now, that's the difference between h of k and the k, these two numbers. With this formula, you can see h of k is another multiple of 3. Yeah. But the h of k, if it's a multiple of 3, what is the consequence? What is the direct consequence of it? Only 1/3 of the slots are used for the pattern, right? Yeah. 0, 3, 6, 9, only these slots, the slot number that is a multiple of 3. Yeah. So if I list the slot number that we can use with this hash function, the 0, 3, 6, 9, 12, yeah, because we do not consider 15, right? Yeah, because the slot number we use from 0 through 14. Okay. Those are the valid slot numbers. Then you can see only 5 of them can be used under this hash function. The remaining 10 can never be mapped by this hash function. 10 slots are wasted under this hash function. So that tells us how bad it is, right? This hash function is very bad. Okay. This simple pattern easily breaks this hash function, make it very bad. Yeah. Waste 2/3 of the space. It only uses 1/3 of the space. 2/3 space is wasted. Okay. Yeah. And we're not satisfied with that. We want to fix it, fix the problem. The fixed problem, you can see if one can develop a better hash function to make use of most of the slots. Yeah. So if it's not 100%, can we use 90% of the available slots with a different hash function? Yeah. So here you can see the problem. How important to break the slots. Break the special patterns. Yeah. All right. So another view. Yeah. So let's try to look at some other patterns. Yeah. So still with n slots, another example, but this time, let's consider n is a power of 2. The special number. We know it's not good. Yeah, power of 2. Yeah. When we do this k mod 2 to the rth power, what would happen? Yeah. Look at that. So the mapping result, what would happen? Okay. Here the pattern, if the given keys have the same last R bits. Look at that. If two keys have the same last R bits, then under this hash function, they are mapped to the same slot, right? Yeah. Because when you mod 2 to the rth power, we only keep the last R bits, right? Yeah. So here, the modular operation here, keep the last R bits. Yeah. If two keys have the same last R bits, then they have the same hash function value, same slot. Okay, that's not good, right? Yeah. So here you can see, if you choose this hash function, it's very easy to break it. Yeah, very easy to break it. Yeah. We do not want to see this problem appears. Yeah. All right. Yeah. So we want to fix it. So, all right. Yeah. All right. So the question, a good choice for division method. Yeah. So when we design our division method, we want to avoid two, what we've found from those two examples. Yeah. All right. A prime number that is not too close to any power of 2. Here, we want to fix the problems from those two examples. The method to fix, we use a prime number here. M slots, right? That M. We select the prime number as the M. Because prime number, you can see we won't have that 15 case, right? That 15, remember, that is 3 times 5 equals 15. 15 is not prime number. So when we choose a prime number, we avoid, the problem we notice from that 15, m equals 15. Yeah. But second, how to break the, how to fix the second problem, power of 2. So this prime number should not be very close to power of 2. So we try to fix the second problem, right? Yeah. And in this way, we can improve a lot. Okay. Yeah. Yeah. But actually, yeah, I mean, the result is better than before, but still, we feel still, it has a lot of room to improve. Yeah. Yeah. And how good it is, people can do experiments, but it is very hard to describe how good it is. Okay. Yeah. All right. So it is possible to create a special pattern to make it perform poorly. Yeah. But here we won't go that direction too far. Yeah. Here, what I like to make the conclusion for this division method, yeah, it is quite limited. Yeah, this division method, yeah, no matter how hard we try, it is still quite limited. Okay, yeah. And as a conclusion, this division method does not perform very well. Okay, yeah. So the next time I will talk about multiplication method. Multiplication method will be much better than this division method. Okay, Yeah, so we can make it more robust multiplication method. Then, so I talk about no matter how hard you try, you can never avoid the possibility that your hash function could map two different keys into the same slot. That could still happen. That could still happen. Then we need to consider the solution. When it happens, what should we do? What we should do, okay? What we should do when the collision happens, we call it collision. Yeah. Two keys are mapped into the same slot. So that's the collision problem. So then we look at a, solution for the collision problem. So then we will complete this topic, hashing topic. Yeah. All right, so let me stop right here.